Okay. Okay, so we will start with our lecture. So let me find my PDFs. Oh, here we go. Oh, first of all, let me share my screen. That would help. Now let me find the PDF of the lecture. Oh, there we go. Okay. Okay, so I believe we had finished the coupling reactions, and look how I'm busy teaching. And now we are on free energy and equilibrium constants. So this is the Gibbs free energy, and then the KEQ is the KEQ we've been doing. And so our gases are going to be partial pressures in atmospheres. The solutions would be in molarities. And so what you're going to do is you're going to write out the equilibrium reaction for ammonia gas plus carbon dioxide gas produces aqueous urea plus water. And then after you write the equilibrium reaction, then you're going to write the equilibrium expression. So first is the equilibrium reaction for the word equation, and then you will write the KEQ, the equilibrium expression. So I'll give you a little bit of time to work on that. Oh yeah, you had to find the urea. It was in your notes. So then the equilibrium expression is what we were doing way back in chapter, I want to say chapter 14, equilibrium. Yeah, chapter 14. So this is our KEQ, products over reactants. We use our stoichiometry as coefficients. We've got molarity for the solution and partial pressures for the gases. So you're going to do the same process. So you're going to write the equilibrium reaction for silver chloride solid dissolves into silver ions and chloride ions, and then the equilibrium expression. So remember to put your phases and your charges. Now go away. Go away. And then this is a KSP. Okay, so we'll go over these together coming up here. Okay, so you want to remember the formula for calcium carbonate, and then always put your phases, solid, decomposes. Here's our calcium oxide solid, carbon dioxide gas. And then the solid does not show up in our KEQ expression. So this is technically a KP. Lead 2 iodide, it's a solid, equilibrium lead ions, iodide ions. You have to know to put the AQ in here because it says dissolves. If you want to put water in here, that is fine. So you could put water above your equilibrium arrows, and then that helps you to see that it's going to be forming a solution. And then this is a KSP. So for aqueous hydrogen ion, you have to remember to put the plus charge. Did you remember hydrogen ion is H plus 1? And then hydrogen carbonate, you have to remember that's -1. So this is an acid, this is a base at equilibrium. And so you're going to get water plus carbon dioxide gas. So the gas will be in atmospheres. And then the hydrogen ion, the hydrogen carbonate will be in molarities. Okay, does anyone need more time copying this down? Okay, so we learned that when we put that little superscript 0, Okay, so there's B, in case you missed it. Yeah, let me know if you have an issue. I have an Ethernet, so I don't know why it told me my internet was unstable, because that's why I have the Ethernet. It's like, you know, everyone on the West Coast is now on their computers. Okay, do you guys need more time for B? And let me know when you're done. Let's put it that way. Okay. Okay, so we learned that when you put that little 0 superscript, so for example here, that means standard state, 1 atmosphere, 1 molarity. But when you do not have it, then that means you're non-standard state. So you don't know what the molarity, what the atmospheres are. But what we're saying is now we have a way to take our standard state free energy, add RT times natural log of Q. This is the Q we've been talking about before, the reaction quotient. And then R is our gas law constant. And then we can take a standard state and find out the non-standard state. So that's what this equation is about. So if we use the KEQ instead of Q, then we can relate the free energy, the standard free energy, to the equilibrium constant. And that's this equation here. So this next example is asking us to find the KEQ for the formation of urea. And so we're going to start with the balanced equation. So ammonia gas plus carbon dioxide gas in equilibrium with urea, this is urea, and water. We're given the free energies, that's this underneath. So you were given this in the problem, and we're given the free energy for ammonia is here. The free energy for carbon dioxide gas is here. Free energy for urea, free energy for water. And then we're doing the products minus reactants. So here's your products minus, and then here's your reactants. And we have to use our stoichiometry. And then here's the free energy that we get. So I'll give you some time to copy this down.
The value we're finding at the moment is delta G.
Yes. So these are the delta G. Okay, these are the delta. Okay, these are the free energies of formation that we were given in the problem. So you notice here it says delta G of urea is minus 204 kilojoules per mole. And so that's here. And then what I would do is I would make a little chart and I would label it. I would not balance the equation for you, but I would give you the chart and I would give you the units. So in the questions, you will have a little table. and it will give you the values. So this is what a question might look like, but keep in mind, I would not put this because I'm not going to balance it for you. That's your job. But I would label it and I would give you the units. And then your first step is products minus reactants. So now we have this. The question is asking for that. So what happened here is I took this equation, divided both sides by minus RT, and rearranged it so that I would have the natural log of the KEQ on one side. And what you need to do right now is take out your calculators, solve for KEQ, and make sure you get this answer. So take a moment to pull out your calculators and make sure that you can use them. And double check. If you get close to this answer, that's fine. You would still get full credit because these are logarithmic functions. So if you use slightly different numbers of significant figures than I used, this number will change slightly. But if you're in the ballpark, you're fine. So please take your calculators out and go through and solve for this.
Yeah, I rounded up one of the answers, so it looks a little different. It still goes to like 240.
As long as it's close, you're fine.
All right. Would you say close is like within like 1 decimal point, or not 1 decimal point, but like within like 7?
240 something.
Yeah.
Yeah, I would expect it to be at least 240s somewhere in there. Okay, you want to be careful with your units. If you noticed here, the free energy was in kilojoules. You need to change that to joules because look at the units in our constant. The units have to match up.
Professor, I tend to not like writing out the whole number for R. So is it okay if I just put that in for R, like when I show work?
What do you mean put it in for R?
I mean, like when I do my equation, I just write it down as R.
Okay, well, I'll just take a point off.
Okay.
You realize I'm in charge. Yeah, you guys can do whatever you want, and then I'll do what I have to do. So yeah, I would just, okay, let me just be real clear about this. I would take off 1, 2, 3, 4 points. Because every unit could be a -1. So that would be like a -4 for not showing this. If this was, say, a 20-point problem, every phase could be a point off. Every unit could be a point off. You could end up owing me more than 20 points. You could go in the negative if you didn't use all your units. Because we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. Yeah, I'm already at -21, and it's only worth 20 points. And then usually 2 or 3 points for this. Show all your units. If that's the only idea you learn, is show all your units. Okay, does anyone need more time copying this down? So what's really nice is if we're given a KEQ, we can find a free energy. If we're given a free energy, we can find a KEQ. So anyone need more time copying this down? Okay. Okay, so this is another example, and we're again finding the K. Oh, did you need more time? Oh, I keep forgetting to check the chat. So just put in the chat when you're done. Okay. Okay, so this is the same problem, we're just practicing, because it's always good to do more than one of these. So it's asking for the KEQ, and if this was a problem given on an exam or a quiz, you would be told calcium carbonate solid decomposes into calcium oxide solid and carbon dioxide gas. So you would have to write the balanced equation. And this kind of shows you how you would be given it labeled, that you have the free energies units. And so this is a free energy for this. This is a free energy for this. This is free energy for this. So all you would be given in the problem is what's above the line here. Okay, so that would be it. That would be what you're given, and then you would have to do everything else on your own. So products minus reactants. And then we use our little equation here. We rearranged it, went from kilojoules to joules. And then, so what I want you to do again is go ahead, copy it all down, of course, and then pull out your calculator and practice getting that.
Professor, for temperature, I just wanted to make sure in equation like this, it would always be implied to be 25 because of the delta G with the subscript of 0.
Yeah, we're at room temperature.
Yeah, thank you.
So on these word problems, you want to make sure you answer all parts of the problems. So inevitably what happens is a couple of students will do all the work and then they'll miss part of the problem. So if this says explain, then you have to put a few words in. So it says explain where the equilibrium lies. That's going to be worth a couple of points. You don't want to lose points because you just forgot to finish the problem. The free response are typically multi-part because they're 15 points. I mean, there's going to be a lot of components. So for this explain where the equilibrium lies, we could look at this. We just need to look at the exponent. The exponent is minus 23, which is, that's so small, my brain can't even figure it out. Like, okay, 22 zeros and then the number. That's really small. What does that mean for the equilibrium? That means and that's what the explain would be. You would just put some words. The KEQ is very small, therefore equilibrium lies towards reactants, or I will accept equilibrium lies towards the left. And so that's answering the part that says explain.
Okay, so could we just put equilibrium lies to the left, or would we have to preface it with KQ is very small, therefore equilibrium lies toward the left?
It says explain.
Okay.
You would have to say something about this exponent.
Okay, thank you.
Okay, let's take a look at the delta G. Okay, so here's our delta G. Okay, so our delta G is positive. And then we're gonna have to go back to earlier in the notes. Okay, so absolutely you are going to want to memorize this. We've got 3 possible scenarios. If the delta G is negative, the reaction is not spontaneous. It gives up, it's spontaneous, sorry, gives off energy. This is how the chemists think about it. They think in terms of the reactants. The reactants are giving off energy. If delta G is 0, the reaction's at equilibrium. If delta G is positive, the reaction is not spontaneous, it requires energy. So memorize these 3. And then let's go back to our example. And where was our example? Okay, so we did that one. It was right here. Okay. Okay, so now we go back and we look at our delta G and we know it's positive. And so we know that the free energy, which I cannot spell, is positive. So we would require energy and it's non-spontaneous. Okay, so according to our delta G, it's non-spontaneous. And we could show that if it's non-spontaneous, according to the delta G, the equilibrium lies this way. And then according to our KEQ, it's very small. And so according to our KEQ, our equilibrium lies that way. So this positive tells us where the equilibrium lies. That would be another way you could explain the answer. Or certainly this very small exponent tells you also where the equilibrium lies. And your arrows better be matching up. So the positive delta G means it's non-spontaneous, and the very small exponent means it's non-spontaneous. So you could draw arrows like this and make sure they match up. If they do not match up, you did something wrong. So I like to draw arrows and I like to explain to myself. But yes, we did everything right. They match up for sure. Okay, so you're going to do this one all on your own. Oh, sorry, to give you the values. Okay. Okay, so you're going to do this one. You're going to calculate the KSP. Okay, so let's start by making sure you got the free energy correct. And then let's check and see that you got the right answer. Okay, it didn't ask where the equilibrium lies, but I just wrote it in for my own benefit. And we see that if we just look at the free energy, and we indicate what that means as far as where the equilibrium lies, it would mean this. And then if we look at our value here, for our KEQ, we see it's very small, which means equilibrium lies this way. And so it matches, our arrows match, which is good. Okay, so anytime you have a constant, you can always use a lot more sig figs because these are constants and they're known to an incredible number of significant figures. So in your book, you're going to see that the constant is 8.314. And so feel free to use that. So the constant does not dictate your sig figs, and we're not even going to worry about sig figs when we're doing these problems. You're going to have to worry about. But if you want to use the 8.314, that's fine. You get close enough. Okay, does anyone need more time copying this down? Okay, you can use as many sig figs as you want on the constant. It's not going to really change the answer. If you want to use 20 significant figures here, it won't change the answer that much. You'll still be in the ballpark. This is what's important, is this exponent. So this is what gives you all the information. This number might be slightly different if you use a lot more significant figures here, but this is what gives you all the idea about where the equilibrium lies. So that's why I was saying, as long as you're close and you're in the ballpark, you would get full credit. And plus, if you used 8.31450, I would see that because you wrote in your problem what your digits were. So I would see why yours might be a little different than mine, because you wrote them all down instead of writing just the letter. Okay, does anyone need more time copying this down? Okay. Okay, so what we're going to do now before we go on to this is let me find my internet. Okay. Okay, so here is my internet. And then here is the class. Okay. And then let me go back. Okay, so instructional content. Okay, and these are the videos that I found online that are excellent. I highly suggest you look at them because the presenter does an excellent job of doing more problems. That is how you get good in this chapter, is by doing more problems. Okay, and then let's find your course. Okay, let's go back to this instructional content. Wait, where is it? That was in week 11. Losing my mind. Okay, well, this is weird. Wait, maybe I'm going to week 12. No, week 11. Okay. Let's try this again. Okay, here we go. Okay. Okay, so we're going to want to reinforce this, what we're learning here. Oh my goodness, this is slow. Okay, so let's see, where were we? Okay, so I thought okay, I think we did that. Okay, so let's go ahead and do this because I think that's where we're at. I don't even know anymore.
The second law of thermodynamics states that for all spontaneous processes, the entropy of the universe, the sum of the entropy of the system and the entropy of the surroundings, increases. While the entropy of the system can be calculated from standard molar entropies, the entropy of the surroundings is more difficult to calculate or measure. Therefore, J. Willard Gibbs defined a new thermodynamic function, which allows spontaneity to be determined solely through the entropy and enthalpy of the system, and not the surroundings. Recall that under constant pressure and temperature conditions, the delta S of the surroundings is equal to the negative delta H of the system divided by the temperature T. This term can be substituted into the equation representing the second law. When both sides are multiplied by negative T, the equation now becomes negative T times the delta S of the universe is equal to the delta H of the system minus T times the delta S of the system. The thermodynamic functions on the right side of the equation, enthalpy and entropy, are both solely dependent on the system. Because both enthalpy and entropy are state functions, a new state function can be defined as negative T times the entropy of the universe. This new term is called Gibbs free energy and is denoted by the letter G. The equation for delta G leads to a new criterion for spontaneous reactions. The difference between the enthalpy change and the temperature, or entropy change, must be less than 0. Delta G is also known as chemical potential because it is similar to the mechanical potential energy of a system. Just as a ball will always roll downhill to lower its potential energy, a chemical reaction proceeds to lower its chemical potential. Thus, at constant temperature and pressure, if the free energy of the system decreases, that is, delta G is less than 0, the reaction is spontaneous. Conversely, if the free energy of the system increases, delta G is greater than 0 and the reaction is not spontaneous. If delta G equals 0, then the reactants and products are in equilibrium.
Okay, so that's what we're talking about, the Gibbs free energy. And then we're going to be talking about this.
For a reaction to be spontaneous at constant temperature and pressure, the change in Gibbs free energy, delta G, must be less than 0. The sign of delta G depends on the signs and relative values of enthalpy, entropy, and temperature. Enthalpy favors spontaneity when the reaction releases heat to the surroundings, while entropy favors spontaneity when there is more disorder in the system. If delta H is negative and delta S is positive, as in the reaction between sodium hydroxide and hydrochloric acid, delta G is negative at all temperatures. Thus, exothermic reactions, where the entropy of the system increases, are always spontaneous. If both delta H and delta S are negative, delta G depends on the temperature. Consider the freezing of water into ice, an exothermic reaction where the entropy of the system decreases. At temperatures below the freezing point of water, the water will freeze spontaneously, releasing heat and becoming more ordered. Thus, reactions with negative enthalpy and entropy changes are spontaneous only at low temperatures. Delta G is also dependent on temperature if both delta H and delta S are positive. A common example is a chemical cold pack, where solid ammonium nitrate dissolves in water that absorbs heat from the surroundings. This endothermic reaction proceeds spontaneously at room temperature due to the increase in disorder of the system. Thus, reactions with positive enthalpy and entropy changes are spontaneous only at higher temperatures. If the temperature were lowered such that the T delta S becomes smaller than delta H, delta G would be positive and the reaction would become non-spontaneous. When delta H is positive and delta S is negative, delta G is always positive and the reaction is non-spontaneous at all temperatures.
Okay, yeah, that's definitely a video you might want to watch again. Okay, then we know how to do this. So we're going to go ahead and watch this also.
The standard free energy change for a chemical reaction occurring under the standard condition can be calculated in one of 3 ways. The first method uses the equation for the standard delta G of the reaction. Consider the formation of calcium carbonate from calcium oxide and carbon dioxide. The standard enthalpy change of the reaction can be calculated from the heats of formation of the compounds in the reaction, and the standard entropy change can be calculated from their standard molar entropies. Using the values from the reference tables, the standard enthalpy change and the standard entropy change for the reaction can be determined. Substituting these values into the equation for the change in standard free energy, the standard delta G of the reaction at 298 Kelvin equals negative 130.7 times 10 to the 3 joules. In the second method, the change in standard free energy of a reaction is calculated from the difference between the sum of the free energies of formation of the products multiplied by their stoichiometric coefficients and the sum of the free energies of formation of the reactants multiplied by their stoichiometric coefficients. Take, for example, the reaction between hydrogen and chlorine gases to form 2 moles of hydrogen chloride gas. Like the enthalpy of formation, the standard free energy of formation of a pure element is 0. Thus, the free energies of formation of hydrogen and chlorine gases are 0, while that of hydrogen chloride gas is negative 95.3 kilojoules. So the free energy of this reaction equals 2 times the free energy of formation of hydrogen chloride gas, or negative 190.6 kilojoules. Recall from Hess's law that for a stepwise reaction, the net enthalpy change can be calculated from the sum of the enthalpies of each step. The third method calculates the net free energy change for a reaction in a similar manner. Consider the combustion of zinc sulfide to produce metallic zinc and sulfur dioxide gas, which can be carried out in 2 steps with known standard free energies. Adding the free energy changes of the reactions gives an overall delta G of negative 98.8 kilojoules. Note that step 1 is non-spontaneous. By coupling it with the spontaneous reaction in step 2, the net reaction has a negative delta G and is therefore spontaneous.
Okay, and then we also did this. So let's take a look at this.
The standard free energy change for a reaction can only be determined if it occurs under standard state conditions, when both the reactants and products are in their standard states. However, most chemical reactions do not occur under these conditions. Under any conditions, standard or non-standard, the relative amount of products and reactants present in a reaction is described by the reaction quotient Q. For reactions occurring in solution, Q is calculated from the ratio of the product and reactant concentrations, with each reagent concentration raised to the power of its stoichiometric coefficient. For gaseous reactions, the partial pressures of the gases can be used in place of concentrations. The free energy change of a reaction is equal to the sum of the standard state free energy change for the reaction, delta G naught, and RT times the natural log of Q. Here, R is the universal gas constant in joules per mole Kelvin, and T is the temperature of the reaction in Kelvin. At constant temperature, the standard state free energy has a fixed value, but Q varies because it depends on the composition of the reaction mixture. Consider the synthesis of ammonia gas from nitrogen and hydrogen at 298 Kelvin. Under standard conditions, which for a gas is the pure gas at 1 atm, the partial pressures of all the components are equal to 1 atm, and the magnitude of the reaction quotient equals 1. Thus, the free energy change of the reaction is equal to the standard free energy change of the reaction, negative 32.8 kilojoules per mole, and the forward reaction is spontaneous. Under non-standard conditions, the components of the reaction mixture may initially have partial pressures of 1.2 atmospheres of nitrogen, 3.6 atmospheres of hydrogen, and 0.60 atmospheres of ammonia. As before, the reaction quotient can be determined from the values for the partial pressures. Substituting for Q into the equation, the free energy for the reaction is negative 45.3 kilojoules per mole, indicating a spontaneous reaction in the forward direction. As the forward reaction proceeds, more ammonia is produced and the reaction composition changes. When the reactants and products are in equilibrium, the free energy change for the reaction is zero, and the value of RT times the natural log of Q is equal and opposite in sign to the standard free energy change. Now, if the reaction mixture contains 0.02 atmospheres of nitrogen, 0.06 atmospheres of hydrogen, and 4.8 atmospheres of ammonia, Q is much larger, and the change in free energy is 5.6 kilojoules per mole. A positive free energy change indicates that the reverse reaction is energetically favorable. Thus, under these conditions, ammonia decomposes to produce nitrogen and hydrogen.
Okay. And then let's see if we can do one more, and then we'll take a break.
Both the equilibrium constant and the standard free energy change can be used to determine whether a reaction is product or reactant favored. For any reaction mixture composition, the delta G for the reaction is the sum of the standard free energy and RT times the natural log of the reaction quotient. When the reactants and products are at equilibrium, the free energy change is zero, and the reaction quotient equals the equilibrium constant. So the standard free energy change equals negative RT ln K. If delta G naught is less than zero, ln K is positive, meaning K is greater than 1. In this case, product formation is favored at equilibrium. The larger the equilibrium constant, the more negative the free energy. Take, for example, the breakdown of dinitrogen tetroxide at 298 Kelvin, in which K is 1.34 times 10 to the 17. Substituting the known values into the equation, the standard free energy for the reaction equals negative 98 kilojoules per mole, and product formation is favored. Conversely, if delta G naught is greater than 0, ln K is negative, meaning K is less than 1, and the reverse direction of the reaction is favored. Consider the breakdown of sulfur trioxide gas at 298 Kelvin, which has a delta G naught of 141.6 kilojoules per mole. The equation can be rearranged so ln K equals negative delta G over RT. Substituting the known values into the equation and raising e to the power of the result, K is very small, indicating that the reactant is favored. Notably, if the temperature varies, the equilibrium constant will also change. The temperature dependence of the equilibrium constant can be derived from the equation that directly relates K to the delta G naught for the reaction. The delta G naught can be replaced by the standard enthalpy minus temperature times the standard entropy. Dividing both sides by negative RT yields ln K equals negative delta H over RT plus delta S over R. This equation is in the form of a straight line, where the natural log of K can be plotted against the inverse of temperature in kelvins, with a slope of negative delta H over R and a y-intercept of delta S over R. If the values of K are measured at two slightly different temperatures, then this graph can also be used to calculate the change in enthalpy, assuming it remains constant over a limited temperature range.
Yeah, that's what we were doing in lab. So, okay. So what we're going to do now is take a 10-minute break so to get some more oxygen into your brain. So we'll come back, say, at 10:15. It's a little more than 10 minutes, but that's fine. So run around, take a break, get some oxygen in your brain because we've got more to do because this is what's coming up next. So come back at 10:15 and we will continue. So I'll just leave this on the screen, but we will come back. So take a break till 10:15. Okay, I'm gonna walk around. Oh, Yes. Okay, well, that went by fast. Okay, so this is what was in the video. And I made a table. I also made different examples. There's also in your textbook, there is a table. So let me find that while you copy this down. Okay, so table 17.3 in your textbook. So this is the same information and the video does a really good job of explaining it. So you might want to watch the video again. So this is exothermic, gain in entropy. And then so your delta G is negative and then spontaneous. And this is an example. You don't need to memorize the examples, but I just wanted to give you different examples in the video or the textbook. And then if you have a gain, like this is endothermic, and you're losing entropy. And of course, if we know the delta G is then going to be positive, that will be non-spontaneous at all temperatures. And this is an example. And then if you have exothermic, but you're losing energy, it depends on the temperature. And so the video explained to you like spontaneous at low temperatures, but non-spontaneous at high temperatures, because then the entropy is more involved. So it's explaining about how the temperature affects the overall. And then this is an example. This would be ammonia plus carbon dioxide making urea. And then the other situation would be endothermic, gaining entropy. And again, as in the video, it explained to you to be non-spontaneous at low temperatures and spontaneous at high temperatures. And then this is the example.
So higher temperatures causes the value to become negative, and lower and lower temperatures equals a positive
For delta G?
delta G. Yeah, for delta G.
Here and here.
Yeah. Thank you.
So again, don't memorize all of these. I would not give you this and expect you to know it. I would expect you to know like these situations. These are great for multiple choice questions.
Yeah.
So you want to remember plus delta S is increase in entropy, minus delta H is exothermic. And I would not ask you to predict the spontaneity of these individual reactions as far as delta G. You could look at the phases and figure out the entropy change. So these are typically multiple choice kind of questions where you're given the different scenarios for the enthalpy and the entropy. Okay, does anyone need more time copying it down? Because we're going to do a problem. Okay, so here's the problem. Okay, so we're asked for the delta G of formation. I'm sorry, delta G at standard state, but we actually have 1,000 degrees Celsius. And this asked if it's spontaneous. And we're also asked for the Kp, and we're asked for the partial pressure of the carbon dioxide gas. So it's calcium carbonate solid decomposes to calcium oxide solid plus carbon dioxide gas. And we're given the enthalpy of formation values and the units kilojoules per mole. And we're just going to assume 1 mole. If we assume 1 mole, then we could just put in the values. And I got lazy, I didn't put the units in. This would be kilojoules. And kilojoules. So it's products minus reactants, which is what we've been doing. So first we calculated the enthalpy, that's this part. And then we were given the entropy. And again, we're going to assume 1 mole, and the values were joules per mole Kelvin. And this is products minus reactants. And again, I got lazy and didn't put the units in. So I'll put them in right now. So I'll give you some time to copy this all down. Actually, I think what I'll do is go ahead and calculate the delta S on your own. And then figure out what to do, what equation to use for this. And this. And here's your temperature. Okay, see if you can figure out what to do next.
You want delta G in kilojoules, correct? That's the units that is
Yes. Technically, as long as you show your units, you would be fine. So let's see if you pick the equation. And then let's see if you got the answer. Okay, so if you got that, now we're going to try to find the KP. So that's your next part of the question, is to find the KP. So you're on your own. Okay, so this is the equation that you have to use. And that's what you should have gotten for your KP. And then you have to answer the last part of the question. You have to answer, what is the partial pressure of the carbon dioxide gas? So you're going to do that next. Okay, so we look back at the original, okay, so we look back at the original question. Okay, we see this is, oh, what is that? I got a spray paint thing? Huh. Okay, so that's a solid. That's a solid. You guys don't need to spray paint the whole thing. How did I get that? And that's a gas. I don't even know where that came from. Okay, so the solids are not in the expression. So that means that your KP expression is just the carbon dioxide, and then you have to go in and put in your units.
And we can keep it at ATM. We don't have to change it to pascals.
You have no choice. You're supposed to put it in ATM.
Okay.
Okay, does anyone need more time copying it down? This is a good question. I can't believe I gave it away. I should have saved it for your exam or your quiz. Next semester, I'll make a different one.
I have the memory of a goldfish, so it's fine. You could probably still use it.
Wow. Yeah, you'd have the whole summer to forget. But this is a really good question because it's combining the entropy, products minus reactants, gives free energy equation, trying to find the KP, and then understanding what KP means. So we're really in the free response questions, we're combining lots of concepts, which is why they're typically 15 points. Okay, does anyone need more time copying this down? Last call. Okay. So we're going to go back to our Canvas course, which is, okay, here we go. And then, oopsie. Okay, let's try this again. Okay, let's go to modules. Whoa. Okay, so let's go to modules. And we're in week 12. Instructional, okay, so week 12, instructional content. Oh, your favorite review, clicker questions. Okay, so please go to the instructional content, week 12. This is going to be your review, the clicker questions, and you've got a quiz next week. So this is helping you to review for the quiz. So these clicker questions are the review of the chapter. So go ahead and get your clicker questions, and I will put you in, I will put you in the groups. Oh, I think I have to stop this share to put you in the groups. We haven't done this for so long. I'm like, what do I do? Okay, oh my goodness. Okay, we're gonna go to breakout rooms. Breakout rooms. Okay. Okay, so it looks like we're gonna have 3 breakout rooms. That's it, 3 breakout rooms. Okay, so please go in your breakout rooms and work on the clicker questions and try to answer them. Try to spend some time on them because this is your review. Excellent. Okay, so who wants to share their screen?
It says host has disabled screen sharing.
Oh my God, I'm okay, let me leave the room and go back to the main Zoom room and fix that.
I think you're muted, Professor.
Okay, so okay, you're good. Okay, I'm just gonna observe for a few minutes. Oh no, I'm gonna go check the other rooms. I'll be back. Wait, you're on 3 already?
Oh, I got started a bit early with these
No,
two.
okay, we're working in groups here. Wait,
Sorry.
you guys do 1? This is for
Yeah.
everybody, not just one person. Who wants to share their screen?
I can share the screen.
Thank you, Victor. I'll be back.
Okay.
Who wants to share their screen?
I'll share it.
Thank you, Young. I'll be back. Are you guys talking to each other or what's going on?
We were just talking, but then we just stopped. So
Oh, okay.
Yeah.
My bad, sorry.
Yeah, I'm just trying to quietly read to myself because I'm still trying to understand this first one. Formation of Does anyone remember what all allotropes are?
Um,
This word.
No, I'll look it up right now.
All right. Okay, which of the following is false? The free energy of formation of elements in their standard states is 0. That's false. That is 100. I'm pretty sure that's false. The entropy of a formation of elements in their standard states. That's also false. The standard entropy of which of the following is false? The standard entropy of elements in their standard. The standard entropy of elements in their standard states is 0. I mean, yeah, I guess that's true. This one is no.
Allotropy or an allotrope would be when a chemical element can exist in 2 or more different forms in the same physical state. So for an example, you would have, say, carbon, you would have it with graphite and then a diamond.
Yeah, okay. Different allotropes of an element have different values of enthalpies or formation. Okay, that one is true. I know for a fact this is true. Okay. Now that I know what that is, the standard entropy of the elements in their standard state is 0. I don't think that's true, but like these two also seem false to me. So okay. The free energy of formation of elements in their standard states is 0. Let me look at this.
Not part of this.
Actually, okay, no, it's C, right? Because I have like the appendix open, so I can look at this, right? For example, silver, its standard state, most people would say is solid, right? On Earth, at least, right? Like at room temperature on Earth, right? The enthalpy is also 0 in this state, along with the free energy, right? So I'm guessing, so basically, so from that alone, I can't say from that alone that it is 0, but then I look at aluminum solid, same thing. Gold solid, same. Boron solid, yeah, same with boron solid, barium solid, beryllium solid. Carbon graphite is the same. Keep going down the list. Calcium solid, cadmium solid, chlorine gas, cesium solid, copper solid. Yeah, all these things in their standard states have their enthalpies and free energy are 0. So I think
Yeah.
it's C.
Yeah.
Yeah. Okay, if a reaction has a negative delta H and a positive delta S, then which of the following is true at equilibrium? Right. Negative H, positive delta S, all right? Negative H, positive delta S. That means the overall reaction will be negative, so it's spontaneous. So if it's spontaneous, that means there's an excess of energy. What does that mean for K?
It's also spontaneous.
Yeah, I know.
Jeez.
Okay, yeah, I know, but I'm trying to figure out what does that
It's possible.
yeah, like what is K's value? Is it greater or less than? Let's see. Okay, when K was less than 1, it also was similar to when delta G was positive, because do you guys remember that? Like, yeah, it would go into the same direction. So I'm gonna guess they're inverse. So I'm gonna guess if delta K is greater than 0, is positive, like is greater than 0 instead of being less than 0.
Right.
I'm gonna guess that would mean that delta G is negative. Okay.
Let's see.
Okay. Well. Oh yeah. Okay. And yeah, that does seem to make sense from a problem we did. Okay. Spontaneous reaction. A spontaneous reaction has an equilibrium constant greater than 1. I mean, wait, what is it? Spontaneous reaction. I mean, we just learned that, so that one's true already. Has a Gibbs free energy value less than 0. Yes, we got that. And C has caused an overall increase in entropy of the universe. Yes, gonna guess so. It is all of the above because A and B are for definitely true. We already proved that in the last problem. A reaction has a positive enthalpy change and a positive entropy change. Which of the following will make it more spontaneous? Adding a catalyst, well, you need, okay, if they're both positive, then at higher temperatures, the reaction is spontaneous. It's spontaneous at higher temperatures. So increasing the temperature, I think, would be the answer, because adding catalyst just increases reaction speed, which I don't think really has much to do with it. And decreasing the temperature is definitely not. So it's definitely increasing the temperature. If I'm looking at that little table correctly, right? Spontaneous at high.
Non-spontaneous at low temperature.
Huh?
Non-spontaneous at low, so would be decreasing it? I mean,
Reaction has positive enthalpy change and positive entropy. Which of the following will make it more spontaneous? So if you wanted to make it spontaneous when it was non-spontaneous, what would you do? I think it's increase, because negative delta G is equal to, negative delta G is spontaneous. Spontaneous, I'm just going to put spawn. And let me use the annotate tool because I think this will help. Yeah. Negative. Okay, give me a second. Less than 0, that's spawn, right? Spontaneous, right? And the equation for this is equal to delta H minus T delta S. I'm not putting the subscripts because I think it's not, I don't want to. Anyways, so you see how T is like, the more you increase T, the more this whole thing increases. Well,
yes.
if you increase this, that'll make the overall reaction negative because it's a positive value being subtracted from a negative value. The larger the negative number, the closer it is to being negative. So if you increase the temperature, it's more likely to make it negative. It's closer to making a negative. Therefore, if you increase the temperature, it becomes more spontaneous.
Got it. Thank you.
Why don't I just use the clear tool? Okay. God, yeah, this whole chapter I remember was not fun. It wasn't that bad. If the molar heat of fusion of a certain substance is 5,000 joules per mole and entropy of fusion is 50 joules per mole Kelvin, then the melting temperature is what? Okay, let me see. If the molar heat of fusion is 5,000, okay. I need to go back all in the notes here because what's it called? This is a phase change thing. Here's the question with phase change. All right. Right. 4.1 joule. Okay. Joules per mole. Okay. So this one is during phase changes. Yeah. So this is a value that you use during a phase change, right? 5,000 joules per mole. I can tell because of the units. Wait. Oh, no. It's this one. It's 50 joules per mole Kelvin. This is, I can tell because of the units, it's mole Kelvin. Then the melting temperature is substances. The molar heat of fusion of certain substances 5,000 joules per mole. All right, so how do you do this? That's an integral. No. Okay. Delta. Okay. Okay, let me see this. Wait a second. Is there a way for me to, so this is degrees Celsius, right? So I need to figure out a way to get Celsius on top. That will be Celsius is 1 degree Celsius, 0 degrees Celsius, 270. Zero 0 degrees Celsius equals 273 Kelvin. Just making sure of that. So minus 273. And how do I get Kelvin on its own? How am I going to do this? I guess the way I would do that is Kelvin, and then what would it be? I need to get Kelvin on top, so Kelvin on the bottom. Kelvin or joules times joules per mole. Okay, all right. This is I complicated this, but this should be. So what we should probably be doing is doing 5,000 divided by 50 minus 273 negative 173 degrees Celsius. I hope that made sense and that wasn't just gibberish, but yeah, basically I didn't see an actual intended relationship for this, so I sort of just used the units to determine, well, this is you know how it takes like 4.184 joules per gram Kelvin to increase its temperature by 1? That's basically what this is, right? And it's I just did, all right, well, if I do an inverse quantity of this, right, that will give me these units and the position I need them in, right? And that will turn and then I just multiply that by this inverse, so that's just dividing it out. That cancels out the joules and moles, and I'm just left with Kelvin, and I just subtract 273 Kelvin in order to equal the value in Celsius. Does that make sense? Oh, okay. I'm just gonna assume that everyone understands. Okay. Question 8. If reaction has started as a standard Gibbs free energy change of negative 100 kilojoules, so delta G, at 25 degrees, okay, standard temperature. Celsius, when the equilibrium constant for the reaction is, okay. All right, well, first of all, this is 1.0 times 10 to the not 6, right? 100 times 1,000.
Maggie.
1.5.
Okay, my goodness, why'd I say that?
Huh?
Nothing.
Right, yeah, that is oh, better put actual units, joules is equal to, I'm just gonna put it down here. Or where's the select tool? Move this whole thing here. Good. Okay. Minus, yeah, 8.31. Okay. Oh God. Man. 8.31 joules per mole, or not mole Kelvin, Kelvin mole. It's not very different, but that, and then 298 Kelvin, and then just multiply all that by a lot of K.
Sorry about that, family. Mhm.
No problem. Okay, that means K is equal to, I'm just going to put like the, what's it called, values here. Like I'm not going to write it all down, but I assume you'll know what they are. Right. Ooh, I made a big mistake here. Put a negative sign. R T. That should give the answer. Okay, so e to the power of negative 1.0 times 10 to the 5th power divided all by negative 8.31450 times 298, 3 parentheses. Okay, let me do that again. It's not that I think the answer is wrong, just syntax error. Okay, right amount parentheses. Okay, K is equal to, why is the screen going darker? It's plugged in. God, 3.3. Oh God, I need to look at this. 3.7. Yeah, 3.37. So that's a positive value is greater than 1. So that means 3.38. No. Okay, I've done something wrong. What have I done? Is that 1 times 10 to the 5th power? How would I just do 100,000? 1, 2, 3. Same answer. Wait, what? Wait a second. Oh, yeah, I just didn't see it. It is times 10 to the 17th. Yeah, I didn't look to the left. Yeah, all right, so that makes sense.
Yeah, I got that too.
Oh, okay, good. I thought I was going crazy. I'm like, where's the 10 to the 17th? All right, clear all drawings. God, I use this annotate tool a lot in like physics. and each time I use it, it's still infuriating because it's a mouse. For any process at equilibrium, the standard Gibbs free energy change is 0. For any process at equilibrium, no, I don't think so. For any process at equilibrium, K equals 1. All right, that would just be, actually, no, that seems, mathematically at least, that seems to be true, because K is equal to E to the power of, I know people like to put the ln of K, but I don't. I just like to go directly to the power of E, not delta K. This isn't physics. Delta G over negative RT. If delta G, oh God, if delta G equals 0, right? That means this whole thing becomes 0, and that equals 1 always. So if a process for any process at equilibrium, and when K equals 1, that means equilibrium. Back to my notes just to make sure of that 100%. Where is it? Where do I have this? Yeah, where was it? Greater than K. Oh, I don't have it written down. I better write that down. K less than 1. K greater than K equal to 1. K greater than 1.
It's on page 72. Well, I think it's page 72.
72. All right.
Under section 4, free energy. Remember, she's to memorize those.
Yeah. Where's component thermodynamics? I have. Okay, I just didn't write that down. That's bad. K less than 1, K equal to 1, K greater than 1. All right, and that's just gonna do shift left, equilibrium, shift right. So if everything is in its standard state, the Gibbs free energy would equal 0. Therefore, the equilibrium would be achieved. So yeah, clear all drawings. So yeah, that should be true. 10. 10. The standard Gibbs free energy change for a reaction is negative 50 kilojoules. Okay, so 50,000 joules. But the concentrations present are such that Q equals 10. I have Q somewhere here. There it is, ln of Q. If concentrations present are such that Q equals 10, then what is the actual Gibbs free energy change at 298 Kelvin? Oh, in that case, so the problem for this, I don't remember going too much into this one, right? We sort of just learned it, but it was delta G equals delta G subscript minus, or not minus, plus, God, RT ln Q. All right, so that would be, in this case, 5.0 times 10 to the 4th. Let me see, 50 times 1,000. 1, 2, 3, 4. Yeah. Okay, times 10 to the 4th joules plus, I'm just calling it R, and this one is going to be 298, so 25 degrees Celsius, times ln ln of Q. It's going to be 10. All right, so 50,000 plus not negative 8.31450 times 298. Do that whole thing, right? And then ln of 10. Okay, that's a bigger number. Delta G would equal to, let me just scale this down. 1, 2, 3, 50, there it is. 5.7. Wait a second. I forgot the negative sign. God, I have to do that whole thing again. Negative 50,000 plus 8.31450 ln. What was it? 10. Okay, different answer. Ignore that answer. It was wrong. It's negative 44. 123.3 if you round up kilojoules. There. Now, there. Okay. Does anybody have a different answer? No? Okay. Question 11. Which of the following is not a spontaneous reaction? Okay. Okay, delta G is 0. Okay, delta G is 0. I think it's 0 there as well. Let me see. God. So positive, wait, not positive, give me a second. ALSO4, yeah. AL. Not spontaneous reaction. So we're looking for when delta G is positive, okay. Okay, ALSO4, where is that? I don't have that on my appendix. That's bad. Okay. AL solid, it's just 0. Enthalpy of that. 3H2SO4. I don't know. This is some number. This is some number. I don't know. I don't have it in my table of values, annoyingly. And 3H. Okay. H2. That's a gas, right? So since this is a gas, I'm assuming this is also 0. Since this is in its natural state, delta G and delta H are 0 for this. Same with this. So it's between these two and these two. And I don't know which one is larger. Because I don't have the value for it. That's so really annoying.
I think we're supposed to be looking at the moles in the states only.
Oh.
Remember?
Oh, okay. Oh, yeah. 2.
Because I remember she was writing SSG, you know, and then we know that gas is more disorder.
So, all right, in that case, oh yeah, so this would be the only thing. This would just be K is equal to P. Oh yeah, okay. And from there we can figure it out. K is equal to P. H2. times, wait, okay. And, then over. Oh God. Okay, so that would be whatever. It's not a spontaneous. God. Okay, what are the moles on this side? 5 and 4. Goes from 5 moles to 4. All right, so. All right. Bigger entropy. Don't know about the enthalpy. This one, 3 moles to 3. Same thing. This is more entropy on this side. This one. I don't know if this one is marked. 2 to 3. Okay, we're going with 2 to 3. Aqueous. This is less entropy. There's 2 to 1. 2 to 2. Aqueous. Okay. This last one is going to be odd. Ooh, okay. Okay, entropy on this side. Entropy on this side. Entropy on this side. Entropy on this side. And this one I can't tell. Might as well be the same to me. On to the H's. Let's see. Oh, great. The H's aren't too much of them, are they? HG. Oh, are you kidding me? Okay. Which of the following is not a spontaneous reaction? Okay. Which reaction needs energy in it? Right? Which reaction needs energy? This one probably not. I don't think this one needs energy. This one I don't think needs energy. This one doesn't seem to need too much energy. Potassium and lead. More entropy on this side. I'm okay. So this is gonna be weird, but I'm gonna say that these two are gonna be our main thing. I think it's one of these two, right? Because since there's entropy on these, since there's more entropy on the reactant side here, and things tend to want to be in a more disordered state, I'm gonna say you don't need that as much energy to get them here. I'm gonna guess they give off energy, whereas these ones, they're already disordered, so you have to make them more ordered. So one of these two. Now, but which one is less ordered? That's the real question. I mean, this has 2 aqueous, and then it goes to an aqueous and a solid. And this has 2 aqueous, it goes to a liquid. I want to say this one just because solids are really just tend to be a lot more ordered. So more energy to get it to that point. I'm gonna say B. But I'm kind of lost on that one. But B makes the most sense to me. E, I'm not 100% sure, but I mean, I feel like I have done this reaction in a lab room before, and I feel like it didn't need much. Which isn't a really good way to look at things, but that's kind of how I looked at all of these of, oh, I've done these all in a lab. How hard is it to get each one of these? And lead almost always is, it's not always great to work with lead. We don't work with lead very often. Which would have a larger entropy? Ice, steam, distilled water, tap water? No, it's steam. Just I'm not gonna. I feel like I don't need to explain that one. We all know gas is bigger is more disordered. For which of the following process will delta S not be positive? Delta S be positive. Following. Okay, so positive means more disorder. Formation of water vapor from hydrogen and oxygen? No, don't think so. Formation of carbon dioxide from carbon monoxide and oxygen? No. Synthesis of ammonia from hydrogen and nitrogen? No. Decomposition of hydrogen iodide into hydrogen and iodide gas? This one, I think it's D. Because all of these, when they combine together, it goes from 2 moles to 1 mole, or it goes from less to more. It goes from more to less. So this is the only one where it goes from less to more moles. All right, question 14. Calculate the standard free energy change for the synthesis of 1 mole hydrogen bromide from hydrogen gas to bromide liquid at 25 degrees Celsius. 1 mole of hydrogen bromide from hydrogen gas. Oh, okay. All right, let me write the reaction. I'm gonna change to green. I like green. All right, standard free energy, 1 mole of hydrogen bromide. H2 gas plus what is it? Bromide liquid. Bromide liquid. And is bromide a first or second? Where is bromide? It's right there. Okay. I feel like this should be an acid, but okay. So those 3 to 2. All right, calculate the standard free energy. Oh God. Okay, do I have all these values? Bromide? Yes, I have bromide liquid. Right. So I'm just got the appendix open. Let's see. This one is 0 for delta G F. Right. 2 HBr. Now I need to go to H. Hopefully I have HBr. H, do I have H? Okay, H2 gas is 0. 2 HBr. Let's see. HBr. No, I don't have HBr, do I? Is it further down the appendix? Ah, yes. These are acid substances. No. Okay. No, nope. Great. That's great. Well, whatever it is, this value isn't 0. It's a hydrogen. This is aqueous. It's not an acid. I don't have the table for acids anyways, so I thought this was alphabetical. No, I do have hydrogen bromide. Do I? HBO3, no. No. Silver bromide. I have cyanide, hydrochloric acid, fluoric, hydrofluoric. Oh no, that's H. Hydrogen fluoride gas. Okay, where's hydrogen bromide? Excuse me, I can't hear you very well. What did you get?
Negative 53.2.
All right. Did you find that in the appendix or oh there?
Yeah, it's on the first page.
I found the gas stage. Okay, I'm gonna assume that I just did it wrong and it's not aqueous, it's gas. Okay. All right. Negative 53. I got. Oh yeah, negative 53.2. All right. Thanks. Well, that's the whole thing for the whole system because that's the only one that matters. And what is it? Calculate the standard free energy change for synthesis of 1 mole hydrogen. Okay, so that just becomes 1 mole. It's just 1 mole times this, right? 2 kilojoules per mole. And then minus 0. There's nothing there. So it's one of these two. These are the same thing. Right? I'm not going crazy. These are the same thing, right?
On mine, it says
Yeah, I'm looking at the same thing too.
instead of B, I think she mistyped.
Yeah.
Okay. I mean, she is in the room, so we could ask her. Okay.
It's a typo. D is supposed to be positive.
Oh, okay. In that case, I'm just gonna.
I'll fix it for the fall. Sorry about that. I thought I fixed it and uploaded it, but it didn't take. I'll have to re-upload.
There. Oh, there.
Aren't you supposed to do? Oh, never mind. The question says 1 mole. Never mind.
Yeah. Choose the false statement. Yeah, choose the false statement if delta H is positive and delta S is negative. Delta G will always be positive. If delta H is positive and delta S is negative, yes, that's true. Because it becomes negative times a negative becomes positive, and it becomes positive plus positive. So this is true. Delta H is negative and delta S is positive. Delta G will always be negative. This is negative, and that's positive. That means that would be a negative, my negative. Yeah, that's also true. If delta H is negative and delta S is negative, delta G may be negative or positive, correct. If delta H is positive and delta S is positive, will always, no, it's not always positive, it's this one. A reaction is spontaneous if delta H is negative. No, if delta G is negative. If they're all negative, no, that's not. Yeah, it's just delta G. It is possible to make a chemical reaction non-spontaneous by adding either a reactant or a product. I mean, I'm not sure. If you add more, well, if it's spontaneous, then it's product favored. So if you add more reactant, then it'll be more product favored. If you add more product, then it will be, I guess you will shift equilibrium. But I guess that could be true. I'm not sure though. That one's a bit tricky. I'm gonna say true because if it shifts equilibrium, and we've seen that equilibrium and free energy tend to be very linked. So if you shift the equilibrium, you should probably shift the free energy. The entropy of the universe is conserved. Yes. Or the energy is, well, I'm not sure the entropy. I don't think everything is always as disordered as it possibly can. So false. What was the relationship exactly? Back in the beginning of the notes, I have this. The first law of thermodynamics. Yeah. U is the sum of kinetic and potential energies of the particles of a system. U is a state function, a property of a system. Yeah, the first law of thermodynamics is on the first page, if I'm correct. Yeah, energy cannot be created nor destroyed. The energy of the universe is constant. Entropy is a measure of disorder. Is the driving force of spontaneous increase of entropy of the universe? Okay, no, entropy is not conserved. Because in one line it says, right, the driving force of a spontaneous process is an increase in entropy of the universe. So if there's an increase there, it isn't conserved, because that would have to mean that there's a decrease in some other place. But if it's the whole universe, then there's nowhere else. So false. Which is an example of a spontaneous process? Ice melts, a liquid boils, a solid sublimes, a sugar dissolves in water. They are all spontaneous. Okay, ice, you need to add energy to melt ice. You need to add energy for that. Right, so it's not spontaneous. A liquid boils, same thing with a liquid boiling. A solid sublimes, that's no. Solid just goes to a gas, like, what is that? Carbon dioxide. It's dry ice. Same thing. It's just not. Sugar dissolves in water. I mean, that does happen on its own. So they are all spontaneous under specific conditions. No, I don't think they are. Or are they? Okay, ice melts. You add some amount of energy for ice to melt. So the enthalpy is a problem. Here it is. The enthalpy values, those aren't negative. No, those are positive enthalpy values.
Just always fine.
Which is an example of spontaneous. I think sugar dissolving in water, because sugar, when you dissolve it in water, you don't really need to heat up the water, right? Like this is sort of how I'm understanding it. When you add heat to ice, it melts. But if you just leave ice in its normal condition, right? If it's already ice, right, then you need to add some energy for it to turn to water, right?
No, I think it's the opposite. Just just get an ice out of the refrigerator and put it outside at room temperature. It will melt. So that makes it at a certain conditions, it will melt on its own, right?
Yeah. Okay.
By
I
the
guess.
surroundings.
Yeah. That's fair. That's a good. Yeah, that would make sense. They all are. Yeah, because all of these under the conditions, like if you just put it in very hot conditions, it wants to be more disordered.
Mhm.
Yeah, that makes sense. That makes a lot of sense. E. Because of the formation of water from hydrogen and oxygen has a negative delta G, a mixture of hydrogen gas and oxygen gas will spontaneously combust. Formation of water has a negative delta G, meaning it releases energy. I mean, combustion is kind of specific, isn't it? It's like adding oxygen. I mean, isn't combustion just adding oxygen to something? Like in a very basic sense. So I guess, yes, you could say that because it is a negative value. Um,
So I'm gonna visit the other rooms, and when you're done, you can just join the main Zoom room.
okay. Or is it?
Okay, so one of the groups is still working and they're almost done. So it looks like the rest of you have joined the main Zoom room. So let me find out who's still, oh, we're just, okay. Okay, so we're just waiting for that one group. Okay, sounds good. Okay, they're almost done. They're on 20. So, and then I will share my screen and we'll go over the answers. I just stayed in that Zoom room the whole time. So it was kind of fun. So I told them to, as soon as they're done, to join, and then we'll go over the answers. And I have to close all the breakout rooms. I hope they're done. They're almost done. They're on 20, so. Oh, okay. They must be done. I'll close it. Okay, so let me share my screen and let me find my answers here. And we'll slowly go over them since we are reviewing for your quiz and your exam. Okay, so, okay, here it is. Go up. Okay. Okay, if I'm going too fast, just let me, just tell me, I'll go back. Okay, this one I worked out. So okay, entropy was, oh, heat given off, exothermic, that's what, okay, so that's what I did. So I used the idea of the heat being exothermic and I did like a little calculation thingy. So I'll leave this up so you can copy it down. So it worked, so I did the calculation and it worked out to give me a positive delta S. So again, if I'm going too fast, just ask me to go back. But that one I just did negative of negative was positive. Oh, okay. This is from the table, the appendix 2. And everything's in reference to the perfect crystal. This is based on exothermic and then gaining in entropy. And so your free energy would be negative, and therefore your equilibrium would be greater than 1. So I basically used the Gibbs free energy equation. And the idea that the delta G would be spontaneous. This is understanding about Gibbs free energy and entropy. And KEQ. This is that video that we watched, that Jove. So you might want to watch that video again because it's really good. And then also the idea of Le Chatelier's principle, if you're adding heat, you're going to tend towards okay. So positive enthalpy. So another way to look at, oh my goodness. Okay, another way to look at this is positive enthalpy. So I figured according to Le Chatelier, if you have a positive enthalpy, that means that heat is a reactant. And so if you're adding heat, then Le Chatelier says you would push the equilibrium this way. So Le Chatelier's also helps you to answer the question, as well as that video if you want to watch that video again. He had to work this one out. Oh, look, there was an equation. I just used the entropy equals enthalpy over temperature for a phase change. You could have used the units too. I just rearranged the equation. Okay, this one, we have equations to work it out. So you could work out to get the number, or you could do it qualitatively by looking at the exponents. But let's go ahead and look at working it out. And again, if you need more time or you want me to go back, just put it in the chat, or better yet, unmute and holler. Oh, yeah. It's kind of a reminder. Yeah, this is those 3 situations you're supposed to memorize. Okay, so this one we have an equation. Okay, so I'll let you write that down, unless you already worked it out. Oh, yeah. Okay, so this, let's just go through one by one, and the answer is E, and let's go through, I'll explain to you the why of it, because this one is not obvious.
Can you scroll back up to 10 really quickly?
Yes, I can. To that?
To one above.
That.
Yeah. Thank you.
Okay, you got it?
Yeah.
Okay. Okay, so back in intro chem, you learned about driving forces. Whenever you took intro chem. Okay, so a driving force for a reaction is if you make a gas. And plus, look at the phases. You have a gain in entropy, solid going to gas. Now, this one is less obvious for the phases, but a driving force also is making a solid, a precipitate. Because the lead is insoluble, so Le Chatelier says we're pulling this out. And according to Le Chatelier A, if we're pulling precipitate out, then we would push the reaction towards products. You're probably going to want to memorize the entropy of the vapor is greater than the entropy of the solution, is greater than the entropy of the liquid, is greater than the entropy of the solid. Does anyone need more time in this? I don't know if you guys are taking screenshots or what you're doing.
Yes, please.
So you can just put in the chat when you're done. Okay, so then we have to look at the other ones, the other reactions. Okay, so we can look at the phases, solution plus solution. When a solid plus a gas. We have both of these are the driving forces. We have a driving force of a precipitate and a driving force of a gas. So even though this is a solid, we have a gas which has more entropy, and plus we have a driving force and a driving force. So Le Chatelet says, yeah, you're going to make this go. This one is a little different. We have aqueous and aqueous goes to liquid, but if you can make a stable molecule, then that will happen. So remember this for OChem. You're going to see this again in OChem. Water is a stable molecule. So if you can somehow form it, that will happen. Plus, the other way to think about it, this is a strong acid, H+. This is a strong base. We know those react. And it's exothermic. So does anyone need more time to copy that down? And then we get to this one. You can't predict the entropy, but it's the best choice because we know everything else is good. Because this is a weak acid in equilibrium with a weak conjugate acid. And we got a weak base. So since all the other ones are going to want to go according to Le Chatelier and the driving force of reactions, this would be our option. Although technically we know this would be an equilibrium. Because it's weak and weak. So put in the chat if you need to copy it down, if you need more time copying it down. Okay. Okay, yeah. Okay, it's a gas. And just memorize that. Oh yeah, I don't know how to move the slides because I'm not really proficient in PowerPoint. So this is the answer for the next question coming up. I know there's a way to move slides, but like I don't know. Oh, that should be gas. Okay, so this should be the question. And so that was the answer for A and the B. So you need to take the word equations and translate them to formula equations and then figure out your sign of the entropy. And so then here's the other ones. So I'll give you some time to copy that down. Okay, so you got that written down? Oh yeah, and you can't tell. Same phase, same number of molecules. You cannot predict, you would need the numbers. I mean, yeah, anyway. Okay, if I'm going too fast, just ask me to go back. Okay, there's a typo on yours, and I thought I fixed it and uploaded the new one, but you have to work this out. And then on yours, it looked like two of them was the same, and I fixed it, but I guess it didn't re-upload. I don't know. Okay, so you would need to have the numbers for this one. And then you would work it out. So if this is a show work question, even though there's zeros, this would be your answer. You would need to show all this. Okay, so you want to show the phases. You want to remember your diatomics. I would give you these numbers, but I wouldn't balance the equation for you. And then this is products minus reactants. And technically, I should have had some brackets here. Maybe I can go ahead and do that now. Okay, so, oops. Okay, you want to be careful when you're doing these questions, because if we go back to the question, your answer was for 2 moles, but the question asked for 1 mole. So put in the chat if you need more time. You know, it took me a whole year to realize I should be using the chat. This is that video again, and that table. Okay, so yeah, this is the table. Back to the free energy equation. So you can see what I did is I took the words and I put them into like the formula for myself. So put in the chat if you need more time. Oh yeah, well, I don't think I need to explain this. I thought you memorized it. This is from your lecture notes. As Le Chatelier. I believe I have an example. Yep, here's my example. So we know that decomposition of carbonic acid is spontaneous, but if you would bubble carbon dioxide gas through a solution, you could, according to Le Chatelier, push it backwards. God, we keep using Le Chatelier all over the place. Yeah, this is just from the chapter.
What was the answer to 17? Thank you.
Yeah, this is about entropy, and like we tend towards entropy unless we put energy into the system. Okay, so this one is like, hey, if it's hot enough, the ice is gonna melt. Okay, last one. Okay, so this one I will show you the why. This is the why. But look at the ignition temperature. So it's saying you need a spark.
Wait, so what was the answer to it? Oh, never mind. I meant for 19.
Yeah, like Rosa was saying, hey, if you put the ice out on the counter, it's gonna start melting. If you add heat, you're gonna boil your liquid. And then, yeah, the sugar pretty much starts dissolving in water. And then if you add more heat, it dissolves more, which is how you're supposed to make your hummingbird. Like
Okay, thank you.
1 part sugar to 3 parts water. And then this one has kind of this lengthy explanation. Okay, so put in the chat if you need more time on that. Okay, so last call, anyone need more time? Okay, we're done. You guys got your money's worth, and as a taxpayer that I pay myself, I got my money's worth, so yeah.